4.5 linearization. We're going to understand the concept of a tangent line approximation and estimate a propagated error using a differential. Okay, so first off, linearization is using tangent lines to estimate values on a curve. Okay, that's the goal of linearization. And the reason we use a straight line is because it's easier. We know equations of straight lines and how to find them. Curves make it a little more difficult. So the idea is here, example 1, we have f of x equals the square root of x, right? My function, my picture anyway, is a little off. I guess when I copied it, didn't copy very well. So just pretend that the picture is fine. And suppose that, you know, x is 4. Okay, so let's say that right here, x is 4. So when I plug in 4, I get 2. Now, if you look at the tangent line at 4, and the number's really close to 4, I mean to the left and to the right, so 3.9 and 4.1 and 4.2, etc., like that. Really, really close to 4. The curve and the tangent, they look almost inseparable, right? Now, when I say, I'm talking about right here, okay? It's almost hard to tell which one is the curve and which one is the straight line. So linearization helps us use a straight line to approximate values that are on the actual curve. And the first example you're going to see, we're actually going to be able to find, or at least approximate, the value for 4.1 without using a calculator, like not taking a calculator and plugging in the square root of 4.1. Okay, so we all know that f of 4 equals 2, but without a calculator, how can we find f of 4.1? So A, we're going to find the equation of the tangent line for f of x when x is 4. So the equation of the tangent line, I need two things. I need a point and a slope. Okay, my point, they want me to use x equals 4, and then the y is going to be 2. My slope, we find that by deriving, right? So my slope, it's going to take me to derive the square root of x, which becomes 1/2, and then the x, well, let me write it down just in case. So x to the 1/2, right? So I bring the 1/2 to the front. And you know what? I should have written, this is the derivative. So x to the 1/2 power, I can't think. I'm sorry. Let me fix this. All right. This is x to the 1/2 power. If I derive this, get 1/2 to the front, x, and then negative 1/2. But it would be a lot better if I wrote that as 1 over 2 square root of x. Okay, that's what I wanted to do. So there you go. So there's my derivative. I know what x is. It's 4. So 1 over 2 square root of 4. And I get 1 over 2 times 2, which is 1 over 4. So there's my slope. So now I write an equation. Y minus 2 equals 1/4 x minus 4. So simplify, get y equals 1/4 x. 4 times 1/4, negative 4 times 1/4 is negative 1, but then I would add the 2 from the other side. So there's my equation. Okay, so now this is how this works. Linearization works. You use the equation of the tangent, so basically a straight line, and I'm going to use that equation to approximate what the value of f of 4.1 is. Okay, so That's my A was just find the tangent line. B says the tangent line you found is approximately the same as f of x centered at x equals 4. What that's saying is that the values I get out of that equation, this one right here, will be really, really close to whatever value is on my function, the green curve, as long as the number is near x equals 4. And 4.1 is pretty close. So use your tangent line to approximate f of 4.1. Okay, so y, or you don't have to write y if you don't want. You can write f of 4.1 is going to be equal to, or actually, will be approximately 1/4 x is 4.1 plus 1. So I have 4.1 over 4 plus 1. Again, I said no calculator, right? Basically, well, 4.1 is, it's a feasible number to do in your head. 4 goes into 4 one time, and then 4 goes into 0.1, 0.25 times, right? So, oops, I meant to write 1. So 1.25 plus 1. And so f of 4.1 is approximately 2.25. All right, so C, use a calculator to find f of 4.1. So now I'm asking you to use a calculator, and obviously it'll be equal, and this is what you should get. It says how close is the approximation to the actual? Okay, so here my margin of error is a little big, but if you look at them, okay, this would be a good approximation for this. Some of the problems are way better, way closer. Some of them sometimes are even accurate, like right on the money. So what we did was we approximated the value of f of 4.1 using a straight line. And versus the actual, it's not that bad off. It's not that off. All right, next. Approximately how much less than 4 is the cube root of 63? Okay, so again, this is basically something we want to do without a calculator. But the cube root of 63 is going to be something yucky looking. It's a decimal. So what we want to do is basically what we just did. I want to use a tangent line. But I want to use a number that is friendlier than 63. Okay, I can tell you right now that my equation is going to be the cubed root of x. Okay, they want me to use x is 63. I want to use one that's nicer. So hopefully if you're good at exponents and you see the 4 right there, hopefully you're thinking, oh, 64. If I use x is 64, the cubed root of 64 is 4. So that'll be my x. And obviously y will be my 4. And I will use these numbers here to write a tangent line equation. Okay, so derive. When I derive this, well, let me just write it over. This is basically x to the 1/3 power. So when I derive it, I'm going to get 1/3, and then x, and then I subtract 1, it's negative 2/3. So it's going to be x to the negative 2/3 power. Negative means the denominator. The 2 is squared, and the 3 means cubed root. So cubed root, and then squared. So that's my derivative. I'm going to go ahead and plug in the 64 because I want to find the actual slope number. So let's see, 3, the cubed root of 64 squared. Okay, remember I picked 64 because the cube root of it was something feasible. It's 4. So this is now 1 over 3 times 4 squared. which is 1 over 3 times 16, which is 1 over 48. Okay, so there's my slope. You didn't notice, this makes the point 64, 4. So I have a point and I have my slope. So I can actually write the equation. So y minus 4 equals 1 over 48 x minus 64. So here's my tangent line. I'm going to use it to approximate the value of the cubed root of 63 by simply plugging in x is 63. Okay, that's another x value. My x value that I'm now plugging in is 63. But first, let me clean this up a little. Y equals 1 over 48 x minus 64 over 48 plus 4. Okay, so obviously the 4, maybe if I convert that into a decimal, or not a decimal, a fraction, right? So 4 times 48, it's not that bad to do. Let's see, 4 or 48 times 4, right? 4 times 8 is 32. 4 times 4 is 16, plus the 3 is 192. Alright, so the 4 is getting replaced with 192 over 48. So then, let's see, negative 64 plus 92. So it's going to be a positive over 48. 192 take away 60 is 132. Take away 4 more, it's 128. Alright, so now this is my tangent. Well, if I want to approximate for 63, I'm going to go ahead and plug in the 63. 1 over 48 times 63 plus 128 over 48. Okay, so I get 63 over 48 plus 128 over 48. And I end up with, what is this? 191 over 48. So that is my approximation. And that's the best I can get without a calculator, right? Because I'm not going to actually convert that into a decimal, even though I could probably guesstimate that it's like 3 point something. Okay, so what they wanted me to do was to approximate how much less than 4 is the cubed root of 63. Okay, so this right here is my approximation, right? I keep forgetting to do that. This is my approximation, right, for the cubed root of 63. Cubed root of 63 is approximately 191 over 48. So what I'm supposed to be doing is finding the difference. How much less? So the difference would be, so 4 minus 191 over 48. Luckily, we already know what 4 times 48 is, right? Because I had to find that earlier. So 192 over 48 minus 191 over 48. So how much less is it? It's 1 over 48, which looks familiar, right? Because of the slope. Okay, so this is how much less the cubed root of 63 is than 4. But if they hadn't asked for that and they had just asked for an approximation of the cubed root of 63, we would have been done right here. Okay. Example 3. What is the linearization of f of x equals e to the x at x equals 1? Okay, so linearization, again, I need a tangent line. I need a point and a slope. So my point so far is 1 something. If I want to find y, I have to plug it into the original equation. So f of 1 equals e to the 1. So y is e. There's my point. All right, my slope. I have to derive. So the derivative of e to the x is, e to the x. So I'm going to go ahead and plug in. my 1, and I get e to the 1, which is e. So my slope is e. So write an equation. Y minus y1, which is e, equals my slope, which is e, times x minus my 1. So y minus e equals e to the x minus e. Add e to both sides to get rid of this one. Oh, but look at that. It gets rid of that one too. So get y equals e to the... Oh, I almost wrote that in the wrong place. Y times e to the... Or y times... y equals e times x. If I look at my multiple choice answers, they wrote it as x times e. But it's all good. All right. Example 4. The best linear approximation for f of x equals tangent x near x is pi over 4. Oh, sorry. The best linear approximation for f of x equals tangent x near x equals pi over 4 is... So I'm looking for the tangent equation. Okay, linear approximation. Tangent line. Okay, I'm going to write an equation. So I need a point, I need a slope. So I have my point, or my x-coordinate. If I want my y-coordinate, I'm going to take my x and plug it in. So I get, let's see, f of pi over 4. So tangent of pi over 4. You should be able to do this without a calculator. Okay, so pi over 4 is 45 degrees. My coordinates here are the square root of 2 over 2 and the square root of 2 over 2. Remember, this is cosine and this is sine. Tangent is sine over cosine. So tangent of pi over 4 is going to be the sine over cosine. Oh look, it's the same number divided by the same number. So my answer is uno. So the tangent of 45 degrees, or pi over 4, is 1. So when I plug it into the equation, I get 1. And that's my y. So there's my point. Next thing is my slope. I need a slope. To find slope, we derive. So I'll do it down here. F prime of x. So the derivative of tangent x is secant squared x. I'm going to go ahead and plug in pi over 4. And I'm going to write it like this. Secant of pi over 4 squared. Okay, so secant, let's see. Let's refresh ourselves here. Secant is the reciprocal of cosine. So I'm going to look at cosine on my beautiful little unicircle thing I drew over there. And it's square root of 2 over 2. Secant is the reciprocal. So the reciprocal of square root of 2 over 2 is 2 over the square root of 2. And then I have to square that. That's why I put the square on the outside. Makes it easier. So 2 squared is 4. The square root of 2 squared. So the square root of 2 squared is just 2. So my answer is just 2. So there's my slope. All right, I have my slope. I have my point. Right? Now I write the equation. Okay, so y minus 1 equals 2 times x minus pi over 4. Now notice, they didn't simplify much of anything. If you look at all the multiple choice answers, it looks like all they did was move over the 1. So y is equal to, they added 1 to both sides, so 1 plus, and then the rest stayed the same. So that's my tangent line, and if I look, answer is D. Alright, example 5. Find the differential. Okay, so now we're into differentials. Differentials, there's actually like a whole course, right, of differentials in college. They call it DiffEqs, differential equations. We don't do too much with it, but we do some stuff. And differentials basically allow us to use dy and dx separately. So when we derive, we don't automatically just do dy over dx equals. What we do is it's kind of like implicit differentiation. We just, if we're deriving an x, we're going to write dx. And if we're deriving a y, we're going to write dy, not dy dx, because we're not being discriminate against y only. Whenever we derive anything, we're going to write its differential. It's really not that hard. All right, so example 5, find the differential dy when dx equals 0.01 and x equals 2 if y equals x to the 5th minus 4x cubed. Okay, so first off, find dy. I am actually going to derive. So I'm going to take my equation. Let's see, y equals, so y is going to be dy because I'm deriving y. X to the 5th is going to be 5x to the 4th dx minus 3 times 4, which is 12, x squared dx. Okay, so that is a differential. I derived the entire equation. But every time I derive something, I tacked on its differential. I didn't just go ahead in the beginning and write dy dx, even though it's the same thing. Whatever. All right, so customarily this is written like this: 5x to the 4th minus 12x squared, and then dx. Okay, only one dx basically. I don't have to write it twice. Okay, now that it's derived and I have dy, or at least what it equals, I'm going to go ahead and plug in the values that I know in order to actually get a value for dy. So remember, they told me dx was 0.01. That's the difference or the change in x. That's what the d stands for. X is 2. Um, I don't physically have y. Excuse me. But I don't need it because I don't have any y's in the equation. But if I did need it, I could find y just by simply plugging in the 2 into the equation, right? Plug in x equals 2. So I repeat, if I needed y, if there were y's, more y's in this equation. Right now all I have is dy. If I had y's, all I would have to do is plug in the 2 into this equation and figure out what y was. Okay. So I'm going to proceed. Okay, so dy, I don't know what that is because that's what I'm finding. 5 x to the 4th. X is 2 to the 4th minus 12 times 2 to the 2nd power times dx, and dx was 0.01. Right. So again, still looking for dy. 2 to the 4th power, so that's 16. So 5 times 16 minus 2 squared is 4. 4 times 12 is 48 times 0.01. Right. 5 times 16, that's 50 and 30. That's 80 minus 48 times 0.01. Last one. 80 minus 48. That's 32. 32 times 0.01. So if I were to do the math on that, it'd be 0.32. So that is the change in y right there. This is my dy. All right. So part C. What have we found? All right. Well, when x is equal to 2, changes to x. Hold on, let me go up. What did x change to? Well, they told me the change in x was 0.01. Originally, x was 2. So when x goes from 2 to x, to x equals 2 plus the amount it changed by, then the y value will increase approximately by 0.32. Okay, so in other words, when x equals 2, y equals, oh, look at that. I need to know what y equals. Remember what I said? If I needed y, all I have to do is take my 2 and plug it into the equation. Right, this right here. So when you do plug in the 2 into the equation, you get 32 minus 32. So y is 0. All right, so back down over here. When x equals 2, y equals 0. Then when x equals 2.01, y is approximately 0.32. Okay? If y had been 4, then it would be 4.32. If it had been 10, it'd be 10.32. Okay? So we just found dy as instructed, but I just wanted to explain basically what we just did. Great. Next. Example 6. The measurement of a side of a square is found to be 15 centimeters. The possible error in measuring the side is 0.05 centimeters, or centimeter, because not even 1. Find the approximate error in computing the area of the square. Okay, they gave us information. Please read the problem and figure out what they're giving us. So I have a side of a square. It is 15 centimeters. There's an error in measuring the side by this much. They want me to approximate the error in computing the area. All right, area of a square is length times width. Squares, all of their sides are the same. So I'm going to stick with the letter S. Okay? S. So S squared. They're telling me that the side is 15 centimeters. They're telling me there's an error in the side, or a change. So I'm going to call that ds. And it is 0.05 centimeters. Find the approximate error in computing the area of the square. Because of that change, there's an error in computing the area of the square. So you're going to take the function area, you're going to derive it. So dA equals 2s ds. So that's my derivative. My derivative is going to help me figure out the error in computing the area. At this point, right, I'm concerned with this. I want to know what is the change in the area, the boo-boo, the error. So I'm looking for dA. So I need to plug in s and I need to plug in ds. So 2, oops, still green. So 2 times 15, remember, because s is 15, times ds. So 30 times 0.05. And then, so like 30 times 5 is 150. Take account the 2 decimal places, so 150. So the change in area, so this is dA. This is the change in area. Right? The change in area is 1.5 centimeters squared. Now, to find or approximate the error in computing the area, right? What I want to do is, I'll just call it error, is I want to figure out what the change is. So 1.5. And then I want to divide that by the original area, what it would have been, which is easy enough. If the original area is s squared and s was 15, The original area would have been 15 squared, which is 225. So my error would have ended up being 0.0066, muchos sixes, right? Right. Now the reason I use a lot of numbers is because sometimes they specifically ask you for the percentage. This problem did not. Percentage error. Okay. If I just wanted the error, 0.007 would have been good enough. But let's say I give you a problem where I want the percentage. Well, the percentage error would be computed the same way. Just go back to elementary school and remember, if you want a percent, you move the decimal back 2 places. So therefore, my percent is 0.667%. Okay? Right. Or 2/3%. Again, I didn't actually specifically ask for the percentage. I just asked for the error. So the 0.00667, which you would, for the purposes of AP classes, could get away with that, 0.007. But if I ever do specify percentage, I just need you to make it into a percent. And that is the that is the approximate error in computing the area of the square. Basically, the change divided by the old area. All right, example 6. When x equals 3, the equation 2x squared minus y cubed equals 10 has a solution y equals 2. When x equals 3.04, y is approximately... Okay, so obviously we have to find the rest. This is probably originally a multiple choice question. I just chose not to show you the multiple choice answers. All right. So right now, they're telling me x equals 3, and when it does, y equals 2. They're telling me that when x equals 3.04, what is y, basically? Right from here, I can tell you that x is being changed by this much, 0.04. So in order to find y, all I really need is dy, because if I have dy, I can just add that on to y. All right, so look at the equation, the function, derive it. So 4x minus, oh, hold on, I almost forgot my differentials. 4x dx minus 3y squared dy equals 0. Now I repeat, I just said that if I really want to find y, the approximation of y, all I need is the dy, and I can just add it to the original y. Well, therefore, that means I am solving for dy. So everything else, I'm probably going to move over to the other side and then plug in. I could plug in now, but I'll just move it first. So, as foretold, I'm going to leave this here for right now. And I'm moving over the 4x dx. So negative 4x dx. Alright, next step, dy. Still trying to get that by itself. Kind of like implicit. So I'm going to divide by negative 3y squared. So negative 4x dx over negative 3y squared. Okay, so dy is by itself. Now this would probably be a good opportunity to go ahead and plug in all the stuff that I do know, because I know stuff. I know what x equals, I know what y equals, and I know what dx equals. So just plug it in. Alright, so dy equals. I hope it's obvious that the negatives do cancel out. They both become positive, so I don't have to worry about that. X, let's see, 4 times x, x was 3, and dx was 0.04. 3 times y squared, where is y? Y is 2 squared. So that's what I'm finding, or that's what I want to compute. So 4 times 3 is 12. 12 times 0.04 is 0.48. And then 2 squared is 4. 3 times 4 is 12. 0.48 divided by 12 is 0.04. A coincidence, I promise. So the change in y is 0.04 as well. I repeat, it's just a coincidence. Okay, so if I want to actually complete the sentence, I guess, or answer what they're asking me to find. When x equals 3.04, y is approximately 2 plus 0.04. So y is approximately 2.04. And that would complete the sentence, I guess. All right, next. Example 8. Find the best approximation in cubic inches to increase the volume of a sphere when the radius is increased from 3 to 3.1. Okay, so again, information. Radius is 3. It got increased to 3.1. So dr, the amount it changed by, is 0.1. They're talking about volume. And volume of a sphere. I should probably... volume of a sphere. I'm trying to find the best approximation to increase the volume of a sphere when the radius is increased. Okay, so volume of a sphere is 4/3 pi r cubed. There's my equation. I'm going to derive it because I want to figure out by how much the volume increased. So that is the change in volume, so that is dV. So dV is what I'm looking for, just like the area before the first few examples. Right, derive. There is only one variable. It is r. Pi is not a variable. It is a constant. So 3, bring it to the front. 3 times 4/3 is just 4. Do the math. 3 times 4 is 12. 12 divided by 3 is 4. Pi is a constant. It stays there. Still being multiplied. And then the r cubed becomes r squared. And I derived r, so dr. So there's my equation. Now I get to plug in the stuff I know. Now dV is what I'm looking for. So 4 pi, let's see, r was 3 squared, and dr was 0.1. So 4 pi times 9, I'll just write it, times 9 times 0.1. All right, make this look a little prettier. The 4 times the 9, that's 36. 36 times 0.1 is 3.6. So 3.6 pi. That is my dV. If this was a part with no calculator, that would probably be my answer. If it is a part with a calculator, I would have to put it in the calculator, and I would end up with, what do I end up with? Oh, I didn't write it down. All right, hold on. All right, so I put in the calculator, and 3.6 pi is approximately 11.3, what was it? Well, either way, I rounded it. 11.310. Okay, so that is how much the volume increased by. The volume increased by that much. Okay, they're just asking me the best approximation of the increase in the volume. They're not asking me a percentage. They're not asking me the difference between the original volume and this volume. Okay, so it depends on what they ask you for sometimes. Okay, next. The edge of a cube has length 10 inches. It seems like it's missing a letter or something, but our word. With a possible error of 1%. Okay, so this example, now we're talking percents. Okay, so the edge of a cube, I could use e. I'll use x, though. I don't want anybody to think it's the exponential function. So the edge of a cube is 10. So x is going to be the edge, and it's 10. It has a possible error of 1%. So x is possibly changed by 1%. So this right here translates to the change in x Now, the change in x is not 1%. It's like I wouldn't write 1%. I wouldn't even write the 0.01, which is the decimal version of 1%. It's 1% of the original size. So it's 0.01 of 10. Okay? So, and you know what? I'll write it. This is 1% of 10. Right. So then this gets me 0.10, 0.10, however you want to write it. Okay, so that's dx. Find the possible percentage error. So my answer is going to be a percent in cubic inches in the volume of the cube. All right, so volume, right? Volume. Let's see, volume of a cube. A cube is basically all the lengths, widths, and heights are the same. I decided to call them x, the sides. So this is x cubed. So that is my function I'm going to derive. All right, so dv equals 3x squared dx. I know what x is, I know what dx is. I'm looking for the possible percentage error in the volume. So this is just going to get me how much the volume got changed by. After that, I'm going to have to figure out what the percentage is. All right, so plug in what you know. So x is 10, and dx is 0.1 or 0.10 or whatever. So 10 squared is 100 times 3 is 300. So 300 times 0.1 or 0.10. So I figure out what that is, and I get 30. Ooh. All right, so 300 times 0.1 is 30. So this is how much the volume changed by. I need the actual percentage error. Okay, so the percentage error. So what you do is, since it's the percentage error of the volume, not compare, but I take the change in the volume, and then I divide that by what the volume would have actually been. Now remember, this is how I would have computed the original volume. Plug in 10, 10 cubed, right? So 10 times 10 times 10 is 1,000. So 30 divided by 1,000, I get 0.03. Now, this is similar to example, what is the one that I asked for a percent? I don't even know. I don't remember. Oh, example 6. Example 6, I didn't specify percentage. So that's why I told you what happens if they ask for percentage. Here, I'm specifying percentage. So the 0.03, that's a decimal. It's not really a percent, right? This is just me dividing 30 by 1,000. So the percentage error is, move this back, 3%. Okay, there's a 3% percentage error. Right, next. Okay, last example. If the sides S of a square is increased by 3%, then the area is increased approximately, and then I have to figure out. Okay, so a square, it's the sides. I don't know what the side equals. Okay, so I have S for sides. ds, which is the change in the sides, is being changed by 3%. So again, 3% is this much. Times however much the sides were, but I don't know what they are, so we're going to call it that. And we're dealing with area. So area of a square is the sides squared. So I'm looking for the increase, the percentage. Oh, sorry. No, just the increase. I didn't say percentage. My bad. All right, so derive. dA equals 2s ds. Plug in what you know. 2. I don't know s, but I do know ds, and ds, kinda, is 0.03s. Let's simplify this a little. 2 times 0.03 is 0.06, and then the s in the s is s squared. So the increase of my area, they didn't ask for percent, is this. So where would that be? C. There you go. All right, do your homework. I don't remember if there was any. See ya. See ya.